Hello, and welcome to week 5, lecture 1. This is the quiz 1 review. The quiz covers topics covered in week 1, lecture 2 through week 4, lecture 2. The topics we're covering in this lecture are vectors, kinematics equations, Newton's laws, forces, projectile motion, uniform circular motion, and relative motion. So vector addition. We know this is important because a ton of physics quantities are vectors. So we have to take into account their magnitude and direction. So as a reminder, when adding vectors, we take the first vector. So our equation here is S equals A plus B. And so we take the first vector, which is A, and draw that. And then we draw the second vector starting at the tip of the first vector. We have vector A, and then vector B is drawn at the tip of A. And then finally, we draw the total vector from the tail of A to the tip of B. Vector subtraction works just like vector addition, but we take the negative of the subtracted vector. So vector A, and then we have negative vector B. So B would normally point up, but negative B points down. Here are kinematics equations in the vector format representing 3D motion. We have the velocity at time t equals the initial velocity plus the acceleration times the time. Then we have the position at time t equals the initial position plus the initial velocity times the time, plus 1/2 the acceleration times the time squared. And then the velocity squared at time t equals the initial velocity squared plus 2 times the acceleration times the displacement. Remember, these are vectors, so you cannot mix the velocity, or you can't mix them, but for example, you can't take the velocity in the y direction with the acceleration in the x direction. Newton's first law of motion says, consider a body on which no net force acts. If the body is at rest, it will remain at rest. If the body is moving with constant velocity, it will continue to do so. Newton's second law says that the vector sum of forces acting on an object is equal to the mass of the object times its acceleration. And this vector sum of the forces and the vector of the acceleration. So the net force and the acceleration are in the same direction. Newton's third law says when one body exerts a force on another, the second exerts a force on the first. These two forces are always equal in magnitude and opposite in direction. And remember, we refer to this as action-reaction pairs of forces. And these action-reaction pairs are acting on different objects. Here's a table of forces we've covered with their relevant equations, if they have them. So we have weight, which is given by the mass times the local acceleration due to gravity. We have normal force, which doesn't have an equation. Tension also doesn't have an equation. Then we have static friction, which is given, or static friction is less than or equal to the coefficient of static friction times the normal force. And reminder for this, what you do, since normal force doesn't have its own equation, is you need to draw your free body diagram, get your equations, and get a formula for normal force from that. Kinetic friction is equal to the coefficient of kinetic friction times the normal force. And I guess one other thing about static friction is the less than or equal to here. It is only as big as it needs to be to prevent motion. And if you think about this with a free body diagram, for example, if we're just like, we have static friction in the x direction and some other force in the x direction, if this part wasn't true, if it was just like always the maximum static friction force, that would cause acceleration in the direction of the static friction force if there wasn't another force like countering it. So static friction is meant to prevent that sort of motion, so we wouldn't want the maximum all the time unless it's counteracting another force. And some things to remember about projectile motion. The initial velocity is usually given at a specific angle from the horizontal. So here we have phi naught as our angle. And that means that the velocity in the x and y direction are given in via trig. So if it's coming, the angle we're given is from the horizontal, that tells us that the velocity in the x direction is adjacent to the angle, so it's going to have cosine, and the velocity in the y direction is opposite the angle, so that's going to be sine. And then there's no acceleration in the x direction, and the acceleration in the y direction is negative g, the acceleration due to gravity. We can also simplify some of our kinematics equations based on this information. So from the velocity equation, velocity at time t equals the initial velocity plus acceleration times time. In the x direction, there is no acceleration, so at any time, the velocity in the x direction is just the initial velocity in the x direction. In y, the velocity at some time is given by the initial velocity in y minus gravity times the time. For position, we have our position equation where r at time t equals r naught plus b naught t plus 1/2 at squared. So and we want to assume that our initial position is x equals 0 and y equals 0 for at least this example of these equations. That's not always true that the initial y position is 0. So keep that in mind, that it could be something other than 0. But if initial x position is 0, then, and since the acceleration in x is 0, the position is just given by the initial velocity times the time. And for y, again, this is if the initial y position is 0, the y position is given by the initial velocity in y times the time minus 1/2 gt squared. And you do not need to remember these 4 equations, okay? I mean, you're welcome to. It might save you a little bit of time. But as long as you pay attention to your knowns and unknowns, you can get these equations from the kinematics equations. So that's where they came from. So really the fundamental thing is the kinematics equations, not necessarily these extra ones. They're more like a shortcut. A little bit about circular motion. The centripetal acceleration that keeps an object moving in circular motion is given by the velocity of the object squared divided by the radius of the circle. And in circular motion, the net force must point toward the center of the circle. And this is given by the centripetal acceleration. And so we end up with, from our sum of forces, we get mass times the velocity squared divided by the radius of the circle. You can also find velocity if you know the radius and the total time for one revolution. So 2 pi r divided by t, 2 pi is all the way around the circle once. So relative motion, we have 2 reference frames moving relative to each other with constant velocity. Observers in both frames are watching a particle p, that's this guy here. The position of the particle with respect to frame S, which is the gray frame here, is given by this equation, and it is the position of the S prime frame with respect to the S frame, which is this vector, and the position of the particle with respect to the S prime frame. And that will give us the position of the particle with respect to the S frame. And the same relationship is true for velocity. So if we wanted the velocity of the particle with respect to the S frame, that's equal to the velocity of the particle with respect to the S prime frame plus the velocity of the S prime frame with respect to the S frame. But then the reference frames cannot be accelerating with respect to each other, so they both must measure the same acceleration of the particle, and that's what this is showing. That the acceleration of the particle with respect to the S frame is equal to the acceleration of the particle with respect to the S prime frame. Okay, that was like speed round of those. Now I'm going to go through some examples from your practice assignments. For the first one, I'm just going to set things up and not calculate everything because it's kind of a long one. And then the other two are shorter, so I should be able to complete those, no problem. Okay, so the first question is question 6 from week 3 practice. And it's a stone is projected at an initial speed of 120 feet per second, directed 62 degrees above the horizontal, at a cliff of height h, as shown in this drawing, not figure 4-44, although it is in the textbook as that. The stone strikes the ground at 5.5 seconds after launching. So we want to find the height of the cliff, the speed of the stone just before impact, and the maximum height h reached above the ground. And I'm just seeing that this is labeled as point A. So the first thing is we're going to work in physics units. We don't work in feet. 120 feet per second times 0.3048 meters per 1 foot. And this gives us our initial velocity is 36.6 meters per second, much better. And so for A and B, we're talking about the same time interval, like at the same point in time. We want to know what H is, or which is also Y final at that time. And then we also want to know what the final velocity is there. So those are both at the same time, so we can write our knowns for those together. So the initial velocity in X is the initial velocity times, and the angle is 62 degrees, so times cosine 62 degrees. Actually, I'm sorry, I'm going to write it as just theta so that doesn't, because I'm not going to fully plug in all the numbers for this one. The initial y is the initial sine of theta. And then we can say that the initial x position is 0, initial y position is 0. Y final is h. X final, we don't know. I guess that wouldn't be in knowns, it would be in unknowns, but that's okay. The acceleration in the x direction is 0. Acceleration in the y direction is negative g, and then the time is 5.5 seconds. Okay. So when I when I get asked for y final in a situation like this, I guess we can look, there's two kinematics equations that we could use. Y final equals y initial plus v and then v naught y times t plus 1/2 a y t squared, and v final squared equals v initial squared plus 2 a y delta y. Because the other equation doesn't have the displacement or y in it, so that one won't work for us. But I'm just going to show you why I go straight to the long kinematics equation in this situation. Because, okay, we know the initial velocity, we know the acceleration, we want this, but we don't know the final velocity at this point. So this equation is not helpful yet. And then we do know the initial position, initial velocity, time interval, acceleration, and we just want y final. So we're going to use the long kinematics equation. Y final, and I said y initial equals 0, so we can ignore that. And then we have the initial y times the time interval minus 1/2 g t squared. And I'm just gonna add in one more thing, the initial sine theta times the time minus 1/2 gt squared. So I'm not gonna solve it from there. You can plug in the numbers, or you already did because this was your practice assignment. But that is the equation you need for part B, or part A, excuse me, and then part B, we are going to assume that we found that y final value. So now we have some sort of value for 8. Okay, and we want to find the final velocity, but we want to think about this as the vector of the final velocity. So that means we need to find it in the x and y direction. And this time we are going to use, at least for x, we want to use this equation, v final equals v initial plus the acceleration in x times the time. Because there's the other equation. Well, it doesn't really matter for x, but we don't know the range at this point. So I wouldn't want to use the other equation. But again, this is 0. So really, the final velocity in x is the initial velocity in x, which is the initial velocity times cosine of the angle. And then we can use the same equation for y, or we can use this equation here. Either one is fine. I'm just going to use the same equation because I was already using it. Maybe I will, just make these y minus gt. So that is the equation we would use for finding the final velocity in y. And then we would want the vector of the final velocity, which is final velocity in y squared plus the final velocity in x squared. And this is going to come out with a negative number, which makes sense because it's, on the way down. So we also want to give the angle here, and we can give it from, I'll call this angle phi since the other angle was theta. And we can give it from the x-axis. So in this case, tangent of phi is going to be the opposite. Oh, I'm sorry. Opposite is y over adjacent, which is x. And so phi is the inverse tangent of those, and those are the velocity in y over the velocity in x. So that's what you'll use to solve those parts of that problem. And then the last part C, I'm gonna add a page. Part C uses different time because we want y max, which is like the peak height, and maybe I'll just draw kind of our cliff. Okay. And we want this h. So there's some things we can say here. We know that, again, the initial y position is 0. The final at this point is h. We don't know what that is, but we know that. The initial velocity is the initial velocity sine theta still. And then the thing we also know is the final velocity here, or the velocity at the max height in y, is 0. That's the thing to remember here. And one thing I just want to mention is that projectile motion, generally speaking, you can take like the total time and divide it in half usually to get the max time of the max height. But this situation is different because it doesn't go all the way to y equals 0. So like the time to get to this position is not the time it would take to get to the ground if the cliff wasn't there. So you can't say that like T max height equals 1/2 T. You cannot say that for this problem. Okay, so, and then we know acceleration in y is negative g. So looking at the stuff we have, we can, and since we don't know the time at this point, we don't know, we can use the one equation that doesn't include time, which is v final squared equals v initial squared. I'm sorry I keep going between not and initial. I'll try and stick to initial. Plus 2 acceleration times the displacement. And let's check. We know this, we know that, we know that, and we want that. Cool, perfect. This one is 0. So we can rearrange the equation and we get, let's see, negative v initial squared divided by 2ay equals the displacement. And I will plug in g here, not the actual number, just negative g, so that those negative signs cancel. And we end up with the displacement equals v initial squared over 2g. And then reminder, displacement equals y final minus y initial. Here that is h minus 0. So the displacement is actually equal to h in this case. Okay, cool. So that is the basics of that problem. Now we're going to do a different or another problem, and I should be able to it's not too long, so we should be able to solve it all the way. So this is from the week 4 practice, and it is question 4, which is from chapter 5, exercise 34. A circular curve of highways designed for traffic moving at 60 kilometers per hour. If the radius of the curve is 150 meters, what is the correct angle of banking of the road? And B, if the curve were not banked, what would the minimum coefficient of friction between the tires and the road be to keep traffic from skidding at this speed? So the first thing I want to do is just get the velocity in meters per second. So there's 1,000 meters in 1 kilometer, and there in 1 hour there is 3,600 seconds. So the velocity is 16.7 meters per second. Okay, so for A, the first thing we want to do, so this is a banked curve, means like on an incline and the car is driving like into the page. Lopsided tires. Okay, so let's tilt our axes for a free body diagram. Tilt it at an angle theta. And then we will draw weight force pointing down, and the angle is there, and then the normal force straight up in the y direction. And we have our x and y components of the weight force, weight y, weight x. And you can see that weight x is the one that's pointing toward the center of the circle. Okay. So, and then we want to look at the sum of forces in the x direction. So sum of forces in x, because that is towards the center of the circle, mass times centripetal acceleration, and that equals just the x component of the weight. So we end up with mass times, actually I'm going to plug in v squared over r for the centripetal acceleration, equals mass times gravity times sine of theta. Because the angle here, that makes y adjacent, so cosine, and x opposite, so sine. And then mass is on both sides, so we're going to cancel that out, which is good in a couple different ways. For one, this is supposed to work for just any cars. So the mass shouldn't matter. And then also we weren't given a mass, so helpful that it goes away. So then we can divide divide g on both sides and take the inverse sign of both sides, and we end up with b squared over gr. equals the angle. And I can plug in for this. We get 16.7 meters per second squared divided by 9.8 meters per second squared times 150 meters. I hope it was 150. Yes, okay. And this gives us an angle of 10.9 degrees, or just about 11 degrees. So that's how the correct banking angle for a car moving at that speed around a curve of that radius. And then for B, it asks if the curve wasn't banked, what would be the minimum coefficient of friction? So again, we draw a free body diagram, but we're unbanked this time, so it's just, the regular level free body diagram. And we have our weight going down, normal force going up, and then the friction force pointing toward the center of the circle. So let's do our sum of forces. Sum of forces in X. Again, that's the one with the centripetal acceleration. And that's going to be equal to the static friction force. And the sum of forces in Y, we're assuming a car isn't accelerating up or through the ground. So we can say it's 0. And that's the normal force minus the weight. And that actually also tells us that the normal force is equal to the weight, which is equal to mass times gravity. And then reminder on the equation for static friction is less than or equal to the coefficient times the normal force. And when looking for the minimum coefficient of friction, we want to look at the maximum friction force. So we actually want when it's equal. Here we go. And we can just take this and we have mv squared over r equals the static friction force, which is the coefficient of static friction times the normal force, which is mg. So then we can divide mass out again, and we get, and divide g on both sides. V squared gr equals the coefficient of static friction, and we get 16.7 meters per second squared divided by 9.8 meters per second squared times 150 meters, and this gives us a coefficient of 0.19. So important takeaway from this problem is actually really the free body diagrams. Like, I want you to be able to do these kind of free body diagrams depending on the situation given, and generate the equations like this. I know I didn't give a y equation in this example. We can still do that. It's 0, and it's the normal force minus the y component of the weight. Okay, last example is problem 5 from the week 4 practice. So we have a disk of mass m on a frictionless table, and it's attached to a hanging cylinder of mass capital M by cord through the hole in the table. And we want to know how fast the disk has to move in a circle of radius r for the cylinder to stay at rest. So let's start with our free body diagram for the disk, we'll call it. And this is actually going to be a similar looking free body diagram to the one we just drew, with the weight of little m, the normal force, and then instead of friction, it's tension that points toward the center of the circle. And then for the cylinder, I guess, we'll draw that free body diagram. There's only forces acting in the y direction. So the weight force of that pointing down, and then the tension force pointing up. And then we want to do our force equations. So for the disk, we have sum of forces in y equals 0, which is the normal force minus the weight. And then sum of forces in X, this is again the centripetal acceleration. So MAC equals the tension force. And then for the cylinder, there is no forces in Y. In X, we'll just put 0. And then sum of forces in Y. So the thing we're trying to do is get the cylinder to stay at rest. So we want its acceleration to be 0 in the Y direction. So then that is the tension minus the weight of this object. And we can add the weight to both sides, and we see that the tension is given by the weight of the big mass, which is big mg. So we also have over here that the tension equals the centripetal acceleration, which is mv squared over r equals the tension. So we just want to set these two equal to each other. Mv squared over r, little mv squared over r equals big mg. And then this question was asking for the velocity. So we will multiply both sides by r, divide both sides by little m, and square root both sides. So velocity is the square root of big M divided by little m times gr. And we weren't given any numbers in this example, so or this problem. So it's just asking us for the equation. So again, the thing you really need to be able to do is identify the forces that are acting and generate these free body diagrams and the equations from them. Okay. So that is your review for the quiz.